So I would ask everyone that it's still upstanding in the back, please find a seat. Let's start the seminar session. So I normally try not to bring a paper with me, but since the speaker is so distinguished, I thought my memory will not work. So let me read some of the aspects of his career. But he's a multinational worldwide citizen. Antonio did his undergrad and his master's in Brazil, after which he moved to the United States to do his Ph.D. in Illinois. Then he did a postdoctoral stay at the University of California in Santa Barbara. So one of the theoretical physics, I would say, meccas, if you can put it like this. Then he became an assistant professor also at the University of California, but this time at Riverside. Then he moved to Boston as a full professor. And afterwards, 2009, if I'm not mistaken, he moved to Singapore at the National University of Singapore, where he is presently in. He holds several positions, so he's a distinguished professor in the Department of Materials Science and Engineering, and also in physics. He's also the director and co-director of two important centers. I would say throughout his late career, if I can put it like this, he has transitioned to doing 2D materials, and he has been one of the leading theoreticians in 2D material science, if I can put it like that. He also transitioned towards more translational sciences and trying to move not only from fundamental sciences, but trying to apply it to the real world and make a change in people's lives. And he holds plenty of fellowships, but I'd say two important ones that I would like to cite is that he's a fellow of the American Physical Society. He's a fellow of the American Association for the Advancement of Science, so AAAS. He's also a fellow of the Singaporean Academy of Science and the Brazilian Academy of Science. So with that, Antonio, the floor is all yours.
Thank you. Thank you. Thank you, Shadi, for this kind of introduction. Good morning or good afternoon, I don't know. Today, I want to talk to you about something that I think it's of interest of Saudi Arabia, okay, which is translating science and technology into commercial products. It's not something that, you know, as scientists we are trained to do. Okay, so as scientists, we're trained to think about the basic facts of nature and how to interpret them and so on. So it's something I have to learn because my background is theoretical physics. So in fact, I work on quantum field theory when I was a PhD student. And today I'm much closer of doing things which are translational than what I did in my PhD. Okay, but most of this was an accident over the course of my career, you know, because when I moved from the United States to Singapore, essentially there was a call from the funding agencies that we should push more towards industry to give back to society what society gave to us in terms of funding. So that was the call, and of course, I was already director of a research center there, and I responded to that. For my surprise, I enjoyed it very much, and I learned lots of things along the way. But I want to give you a little bit, before that, I want to give you a little bit of a history of what we have done. So the Center for Advanced 2D Materials was created around 2010. At that point in time, NUS was ranked number 31 in the QS ranking of universities. So now in 2021, we started the Institute for Functional Intelligent Materials. So this institute is co-directed with Konstantin Novoselov, who got the Nobel Prize in Physics in 2010 for the discovery of graphene. He's my colleague there. And you can see that the university has jumped from 31 to 11, and now he's ranked number 8. We just got these rankings recently. So the university was in exponential, let's put, growth during this whole period that I was there. And in terms of funding, for instance, this center, it was around $100 million. So starting from the National Research Foundation and from the university. And the second one is $250 million. So half from the university, half from the Ministry of Education. So the investment that Singapore has put into, research it's very big. Okay, I don't know the numbers for Saudi Arabia, but at least in Singapore, they are pushing very hard on that. Why? Because Singapore has no natural resources. Here, at least, you have oil. There is nothing. There's not water, there's not oil, there's no agriculture, nothing. Okay, so the country needs to invest in research to create technology, to create businesses, to create products. This is what keeps the country going. Okay, so that's why they do that, because the only, let's put this way, the only starting point they have is people, right? So they have to invest in people. And to invest in people, you have to invest in education. You have to invest in research. So Singapore is a kind of an example where you can go from nothing and become quite wealthy if you do make the right choices in terms of where you put your money, right? So right now, the first center, the 2D materials, was essentially to explore really materials. Physics of 2D materials was in the early days of graphene. Graphene, as you know, the Nobel Prize is 2010. It was discovered in 2004, right? So it was in the early days. And this new institute is actually more like taking materials and working with these materials to add functionalities, and for that we use machine learning and artificial intelligence. So it's an evolution, let's put it this way, in terms of ways you work with materials. So at the center, a few years back, we essentially start working on this connection between research and industry. Okay, so 10 years ago, there was a shift, as I was explaining to you, for us to move in that direction. So the last 10 years, we have been working on that. So how can I keep doing basic science, okay? But how can I get the results of that basic science and transform into something that brings value back to society? Okay, so we have to create the whole framework for that in the last 10 years. And I have to say that, at least from my perspective as director of the center, we're very happy with the outcomes. And today I want to tell you a little bit about those outcomes. So in terms of equipment in space, you guys here are doing very well. You have a lot of equipment, a lot of space, a lot of labs. Singapore is a tiny island. Okay, 700 square kilometers with 6 million people living there. Okay, so we don't have the luxury of space. Space is extremely expensive in Singapore. Okay, so we have to work with way less space than what you got here. But we try to maximize that use. We try to bring that use to maximal productivity, even though the space is not that big. Okay, so of course we have all these things you need to do, nanotechnology. So we have our own clean room, 1,000 square meters of clean room where we can do nano and microelectronics. In that, we have our facilities have around 200 scientists who use that from the several different faculties into the university. Faculty of Science, Faculty of Engineering. Okay, so it's heavily used, in fact. So in the center, we had these 4 pillars that we have been exploring over the years. Of course, graphene. Graphene today is more of an industrial problem, not, let's say, a basic science problem. But there is a lot of industrial things that we do with graphene. 2D materials, which are materials other than graphene, like transitional metal dichalcogenides, phosphorine, and so on and so forth. Then we have devices. We have a group that does essentially device application. And then we have a theory group. Okay, so we use the supercomputer facilities in Singapore for that. So you have essentially, self-contained system to work all the aspects of the, science of materials. So we have been able to attract extremely bright people to Singapore because we have those facilities, we have those capabilities, we have that, people. So scientists are always looking for their colleagues. What attracts scientists to places is who is there. Way more than the facilities themselves. Without the facilities, you cannot do anything. But, it's your colleagues that makes you move further. They push you to become better. Okay? In fact, one should want to have people who are better than you, so you move forward. Right? So, for instance, 3 years ago, Konstantin Novoselov, who got the Nobel Prize, moved to Singapore. We attracted people from the US, from other parts of the world, because of that. So essentially, to explain to you what we do as a translational center, right? So we created an Office of Industry and Innovation and an Industrial Development Lab. So these are inside of the center, and these 2 pieces of the center, they are focused completely on entrepreneurial industrial projects. Okay? So when people are hired here, we tell them, you're coming here, but you're not going to write a single paper. And when they come and they accept that they're not going to write any papers, the mentality changes completely. So just to give an idea, they didn't write papers, but they wrote 200 patents. Okay? So, and the reward is not the academic reward, like, I'm going to publish my papers and I'm going to become a big professor and, get the Nobel Prize or anything like that. They realize that the outcome of this, if successful, is that they are going to create a company and they are going to become rich. Okay, so it's a completely different way of thinking inside of the university. Okay, because traditionally, this is not the goal of a university. So there is a need of, it's required to change the mindset of people when they come to work in an environment like that. Because their tendency is to keep doing what they always done and what their advisors have been doing for a long time. Right? So, but if you change the rules of the game, people adapt. This is the beauty of people, right? So that people are capable to adapt to new situations and they can thrive, when they have the right mindset to do things. So we spinned off several companies in this, and more recently we spinned off a venture studio. So a venture studio is essentially a hybrid between investment company and an incubator. Okay, so essentially you have people not only put the money as an investment firm into a company, but you also have people who help the company to grow inside of this company. So this is a way that we found to help the companies that we are creating there to actually grow. So even with some setup like this, the amazing things that our academic output is the best in the world. Okay? Even with those constraints. Okay? So for instance, we publish more than 1,000 papers over the years. We have a very high impact factor, better than many other 2D centers around the world, including the one in Manchester, where Novoselov came from. Okay, so I'm very proud of this. Why? Because not everybody here is doing translational research. Okay? A lot of people here are still doing basic science. The communication between the people who do basic science and the people who are doing the industrial work is what makes things go fast. Right? As long as people know, what they have to do, okay, everything falls into place. And that's the beauty of this. So we have been doing very well academically over the years. Okay, so in terms of invention disclosures, right? So we produce a lot. This is not updated. The numbers are bigger than this. So we have lots of invention disclosures, and then, of course, the number of patents, licensed patents, is way less because you don't license everything you patent. Okay, but our rate is actually higher than in many places. Okay, including in the United States. Okay, and we have essentially all over the place. The patents are all over the place, from fabrication process, and actually this is our strongest suit, which is the materials that we work with, we produce them. Okay, so being able to produce the material gives you an edge, a competitive edge when you go to the commercial side. If you're using somebody else's product, somebody else's material, most of the time you don't know what you're getting. But if you produce your own material, you know exactly what we are working with. And I think that this is key for working in material science. Okay, being able to control the production of your own materials. Okay, and characterize those materials and understand those materials in great detail. And so these are examples of things in our pipeline. So we have worked on construction. I'm going to talk about that, which is a bit odd for someone who does nanomaterials, but actually our experience in nanomaterials helped us to develop a new type of concrete. I'm going to talk about that. Coatings, composites, electronics, batteries, medtech. I'm going to show something on medtech, membrane technology, and even cosmetics. Okay, so very broad range of things. And with all these topics, we have companies, spin-off companies that have been created. Okay, so our choice is not to license directly to the industry. Okay, our choice is to spin out a company and then let this company grow on its own. Okay, it's a choice that we make. Okay, so in principle, we could have produced technology for Aramco. Okay, but we decided not to do that. We decided first to create a spin-off, and a spin-off decides what to do. So we have done all these things. So I'm going to talk about three projects that we are developing there to give you a flavor of what we have done. One is in Urba-X, which is a company on green concrete, okay? Excellium, which is batteries for space application, okay? And Nanomolar, which is a company on biosensors, okay? So this is a broad range of complexity in terms of the science and technology, but gives you a good flavor of the things we're doing. But besides that, we have many other spin-offs in the pipeline, okay, in different areas, okay? And we have been working with different companies and venture capital and so on and so forth. So it's quite broad. So let me talk about Urba-X first. So the idea of this came with the issue of sustainability. Okay, so this is the lab, it's the Industrial Development Lab, so we have all the equipment to do construction materials, test these materials according to ISO norms. So this is also very important because when you go industrial, you need to follow standards from the industry. You cannot just get a material and say, okay, this is my material, take it. You have to test and make sure that what you are having there will be approved by the industry, right? So we do this all in-house. So this is actually the inspiration for this, as of course the petrochemical and the construction industry are responsible for 35% of all the carbon dioxide which is generated today. Okay? The construction alone is around 10%. Okay, so the traditional construction material is called the Portland concrete, or OPC. Okay, so this is the concrete, I don't know if you know, it's a material that was created at the Industrial Revolution. So it's a product of the 19th century. Okay? So it's a product, the first patent on Portland concrete dates from, I think, 1800s. So, and this is the same concrete that we use today. Everything you see around you here is made with this concrete, which was invented in the 1900s or 1800s. So think about that. What was going on in the 1800s? People didn't care about pollution at all. So they just wanted results. So they would essentially put waste everywhere. They didn't care. You throw waste in the air, you throw waste in the ocean, you throw waste in the sea, in the rivers, and it was going to take care of itself. Now we know that this was a very bad choice because we are paying the price of the Industrial Revolution choices. Okay? And just to give you an idea, 1 ton of concrete puts 1 ton of carbon dioxide in the atmosphere. Okay? And the amount of concrete in the world is gigatons. Okay? So all this CO2 is being launched into the atmospheres, into our lungs. Okay? So for us, the idea is that how can we help contribute, okay, in that area? And the way we went there was non-traditional, okay? People have been using clays for millennia to make pots and pans and things like that, right? So clay is a material that's everywhere around the world. In this class of materials, okay, it turns out that they are two-dimensional. Okay, so many people don't know that. These aluminum silicate clays, like kaolin and metakaolin, essentially they are layered materials. They have atoms sitting in layers. Okay, what we did was to use all the techniques of 2D materials that we learned from graphene, and then we apply to these clays. Okay, so, and what we learn is essentially functionalization. So functionalization of a 2D material is a way to modify the molecular atomic structure of the material by chemical means. Okay, so we apply exactly the same strategy to these 2D materials, and from this material, we produce a new material that has nothing to do with the original one. So this is an electron microscope picture of how does a kaolin looks like. If I can get the pointer to this, maybe here it's better. I don't know why. Okay, can you see? So this one is metakaolin. You can even see the layers. Okay? And then you can exfoliate this metakaolin to not monolayers, but extremely thin layers. When you do that, you get a lot of surface that you can play with. Okay? And there is when we do the functionalization. When you do the functionalization and you react this, you get a new material which is three-dimensional, okay, which has very little resemblance with the initial material. This is the material that we produce. So we have a patent and about this, how to do this, okay? And this is a trade secret, by the way, because it's a process patent. It's a process patent. So process patent, you should never write it. You should keep it a trade secret because anyone in the world can copy you. And it's very hard to prove that, you know, they copied. Okay, so for the company that we are starting, this is actually a trade secret, how to do that. So then you go and you do traditional construction stuff. So essentially you take aggregates, you take sand, you put this in water, you mix, and you let it dry, and voila, you get your concrete. Okay, but one thing that we also doing is that we're using waste, okay, as a construction material. So we take slags, okay, from different industries and use it. So Singapore, as I said, is a small island, and it produces, being a rich country, it produces a lot of trash, okay, and the landfills. So Singapore essentially built islands around Singapore to dump all the trash. Okay, but these landfills are getting filled. And they know that, you know, eventually, you know, there's no more space. And Singapore has no way to expand. Malaysia and Indonesia will not allow Singapore to grow beyond its size. So they have to find a way to deal with this waste. So the solution of choice is burning. Okay? So you burn this, you make this into an ash. Okay? And then, of course, you have to get rid of the ash. Right? So what we did is that we take the ash and use this as an aggregate to this material. Why we do that? Because in this ash there are chemicals which are good for our concrete. We know that. But now we imagine, depending on the type of trash that you get a different chemical composition. The amount of metals, the amount of oxygen, the amount of carbon changes from trash to trash, right? So one of the problems we have is that every time we get a different type of trash, we have to change the recipe for the concrete. And then we're doing this by trial and error. And as you can imagine, for every different trash, it would take 6 months to 1 year to get a new recipe. Okay? So then we said, okay, let's be smarter than that. And what we have been doing now is using AI to accelerate this process. So what we do is this: we receive the trash, we do a chemical analysis, and then we have a huge database of different compositions and so on. And then we target, say, the compressive strength of the concrete. And we try to maximize that compressive strength. So this is what's done. So we collect data, we do the model training, and then we do the model validation in the lab. So there is a cycle that goes like that, that allows us to adapt very easily to different types of trash when we get to make the concrete. So this is a strategy we have been using, and it's working extremely well. So this is an example of some innovation that we got out of this exercise. All the concrete that you see here uses river sand. Okay? And this is a huge ecological problem. Okay? People have to dig rivers to get the sand to build all this infrastructure. why one cannot use desert sand? Saudi Arabia has plenty of desert sand. Why this sand is not being used for construction? It has to do with the nature of the desert sand compared to the river sand. Desert sand is very smooth because the sand is being worked by the weather, by the wind, and so on. It's very smooth. And Portland concrete, okay, do not adhere to smooth surfaces. You need rough surfaces. Okay, so it's useless unless you change the surface of the sand. But to change the surface of the sand, you have to pay energy to do that. Or, either electric or chemical or mechanical, doesn't matter, to make it rough. So you make something cheap into something expensive to make something cheap again. Right? So economically, it's a difficult proposition. So on our side, we said, no, we want to take sand as is and produce this concrete. Okay? And here is concrete produced with sand that came to us from the Emirates. We just went, we're on the road from Dubai to Abu Dhabi. We just came out of the car, collected the sand, and brought to the lab, and we made concrete. Okay, and that's how the concrete looks like. And this is a comparison between the normal concrete, this is red, with the same sand, okay, and our concrete with the same sand. And you can see here that the compressive strength essentially goes to 0 after 28 days for Portland concrete. So it means that if you take desert sand from Dubai and you put on your concrete and you make this structure, the building will fall down in 28 days. Okay? But in our case, you see here that the compressive strength continues to increase after 28 days. And actually tracks down our concrete with river sand. Okay? So that means that, okay, we have something unique here. Okay, so just using a raw material, but with a new technology, with a new material, a new approach, you can get something of value. All right? So, this material is amazing. It can be used for fixing cracks. So, Portland concrete cracks very easily because it's a porous material. Okay, so in the weather, especially here, I'm sure that all the structures here are fully cracked. The traditional way to fix that is to use petrochemicals. So essentially you take epoxy resin and then you fill the crack with epoxy resin. What's the problem? Epoxy resin does not resist to ultraviolet radiation. So after a while, that thing will completely disintegrate and you have to come back and apply again. Okay? So our material can be used, and of course it's totally insensitive to ultraviolet radiation. So it's a binder that can be used on traditional Portland concrete. Okay, and in fact, the company is going that direction. It's not going to the direction of structural applications. It's going to the direction of applying this for fixing problems with traditional Portland concrete. So this is a fire barriers and all these things, and we work with different types of, we have been using fibers, and also there is a lot of stuff that you can do with this. So sealing and grouting, surface coating, surface impregnation, material encapsulation. For instance, we're working with the Public Utility Board in Singapore to encapsulate their waste with heavy metals, because they don't want these heavy metals to go into the water system. So the way to do it is that you encapsulate it with this material, and then you reuse this material for construction as aggregate. Okay, so these are the things that you can do. We're using this for coastal protection. We're producing these sea urchins to put on the sea. The idea is exactly the same. It's essentially that Portland concrete, if you leave in the ocean, it will disintegrate with time. okay? This material doesn't disintegrate, okay? It's porous, but it's not connected, so the water never really infiltrates the material, like in Portland concrete. Okay, so we can use for that. We're working on that. So this is something that is ongoing right now. We're working with several companies to actually bring this discovery of how the functionalization of the original material to commercial product. But definitely, we're taking a very old material, clay, and transforming it into something completely new. Okay, using all this nanotechnology weaponry. Okay, so let me talk about batteries because I know there is a lot of interest here on energy. I was talking to Professor Hussan about this. He has his research center in this area, and like him, we are targeting niche problems. Okay, so we have our own battery lab, completely funded by the industry, by the way. So the Singaporean taxpayer didn't put a single dollar into this. It was completely funded by the industry. So we have the capability of starting from the chemistry, basic chemistry, to the final product. Everything in-house. We have a pilot line inside of our labs to do that. Okay? And our focus has been space. Why space? Because the problem of putting things on the space is the problem of fighting gravity. So the cost of putting something out there is proportional to the mass that you want to put there. Okay? It's a problem of really playing against gravity. Okay? And once you put there, of course, you want this to last as long as possible, because you're not going to have an opportunity to send it again or send a spaceship to go there and fix if there is a problem. Right? So it's long. You want long lifetime. You want resilience because you are under radiation, cosmic rays, all these things bombarding you, and you want high density, low weight, high density. So this is the standard today. This is a French company called SAP. The only thing they do these batteries for satellites. Each battery costs $1 million. Okay, these are very expensive batteries. Okay, and they only live for 12 years. Okay, the lifetime today, the lifetime of a satellite equals the lifetime of its battery. Once the battery is dead, the satellite is dead. Okay? So the question is, can we get more lifetime out of these satellites? So this was exactly the problem that we put to ourselves. Can we increase this? And we achieved that. So we invented a new type of electrolyte for this kind of batteries, and also for lithium-based batteries that can go up to 20,000 cycles. So we have tested one battery for more than 4 years now, cycling it, okay, more than 20,000 times. Normally, a battery lasts 1,000 times. Okay? So the whole goal was to increase that. But as extra, like they say, the cherry on the top of the cake, the extra thing is that we got 10 to 15% increase in the power density at the same time. There are very good physics reasons for that. I don't have time to go over that. But essentially, we increase the lifetime and we increase the power density at the same time. So this is an example. So this is traditional, here. So this is a traditional battery, okay, I think it's NMC, and after 2,000 cycles, it's considered dead. After, below 80 capacity retention, the battery is done, okay? And our first technology, the first time we tried, we already got 12,000 cycles, which is equivalent in 32 years of operation of the battery. Okay, we have improved this technology. We already are at 20,000 cycles, 45 years So you put this battery there, the satellite will live for 45 years. But after 45 years, the technology of the satellite is already obsolete because the satellite technology is moving. But at least you don't have to worry that the satellite will be dead after 12 years. Okay? So this is an example of what we've done. We are working with Airbus on this. Okay? So they are very interested in this technology. This is the last example I want to give, nanomolar. So this is a completely different approach. This is to healthcare. Okay? So, as I don't know if you know, but 10% of the world population, on average, suffers from diabetes. Okay? In Southeast Asia, okay, in countries like Indonesia, this is already reaching 16% of the population. And this is a very serious problem because diabetes can lead to death. It can lead to amputation. Okay? It can lead to many, many, many problems. Okay, and one of the biggest problems with diabetes is testing. Because the way to test diabetes is the person has to prick its finger 4 to 7 times a day and measure the glucose level. Okay? If you have children, try to convince your children to prick the finger 4 and 7 times a day. You get a nightmare at home. Okay, so it's a serious problem to do. You have to do invasive, measurements to get there. So the idea is that could we develop a non-invasive method to help diabetic patients? And this is a movie. I'll let you.
Okay. Hi, ma'am. It's your turn.
Hello, come in please, come in. Take a seat. So, let's have a look. Oh no, this won't be necessary today. We will use this. There you go. Alrighty.
By the way, this is the actual device. It's not a gimmick. It's really the device that is used.
Okay.
So it sends the result to your phone by Bluetooth, the glucose level.
Wow. This is very good. Really well done.
Thank you. Thank you.
The whole idea here is to, okay, so this is also related, but it's not for glucose, this is for lactate. So now instead of saliva, it's going to use sweat, the same sensor. So the result comes out in minutes. So lactate is very important not only in sports, but also in emergency room in hospitals for the measurement of sepsis. Okay, so if someone is coming with a septic shock, the first thing they do is to get blood from the person to measure the lactate level. And usually this could take hours to get the result. Okay? With this sensor, it can get the result in minutes. Okay? And this is based on graphene technology. So essentially, our sensor is graphene based and it's extremely sensitive. So the idea of all this, the technology, is to avoid this dealing with blood, okay? Dealing with blood, and all the logistics associated with blood. Okay, so when you go to a hospital, take blood, it may take days for you to get your result back. The idea here actually is not to replace blood, but it's more like a preclinical measurement. So you go there, you measure. If everything's okay, there is no need for you to take blood. Okay, so you go home, everything's fine, right? So this is this sensor. It's what we call point of care. So in fact, you could have this in your own house and send your measurement to your doctor via Bluetooth. So your doctor can follow exactly what's happening to you. Okay? So this is, I even brought a prototype. Someone wants to take a look. I'll be glad to show. So this, we have a pilot line to produce this in our labs. Okay? Because of graphene, we're only able to do this because of graphene, because graphene is extremely sensitive to chemicals. So by controlling the electrical resistance of the graphene, we know exactly the amount of chemicals there. Our precision today is picomolar. So to give you an idea what's a picomolar, because it's hard for people to visualize, 1 picomolar is equivalent to 1 gram of salt and 100,000 liters of water. So what I'm saying is this: if you take a gram of salt, put in 100,000 liters of water, and you put a sensor there, the sensor will measure it. It's that good. Okay, so I think it's even record holder. So this example of things, lactate and glucose, we have a broad range of detection. We can detect in the millimolar range with picomolar accuracy. Okay, so not only, but we can, essentially we measure sodium, potassium, cholesterol, cortisol, anything we want with the sensor. This is a very, very, very powerful sensing machine. So that's what I'm saying, it's extremely robust, it's very easy to use, and it's very, very accurate. So this is a comparison between our measurements with sweat and comparing with the measurements in blood. Okay, in fact, for certain biomarkers, we get results which are better than we would get with blood. All right, so let me conclude. My time is up. So this is all coming from an experience on 2D materials. Okay, so this was built over 10 years, creating a certain methodology to approach problems, right? And bringing together basic science and entrepreneurial people, okay, working together in the same environment, all right? And the potential for us is limitless. I mean, I think we're only limited by our imagination on what we can do here. And I think this is just the beginning, okay, of something that is going to be even bigger. I want to thank you very much for your attention and for inviting me here. Real pleasure. Thank you.
Thank you very much, Antonio, for this great talk. I think it opened a lot of everyone's minds. So we are open for questions. I will get there. It's just that I'm slow.
Hi. Well, I have one question. Okay, we know that Singapore is a small island and there is a lot of people there. And you say that the solution is like burn trash. So what happened with the pollution and the people? Because people smell, breathe. So
I'm sorry, do you want to know what the people in Singapore think of this, or?
No, for your solution for burning the trash and what happened?
The trash.
Yeah.
So yes, they're burning trash, and the landfills are getting filled, and they are going to have a real problem. It's a rich country, right?
Yeah.
In principle, they can export trash to another country to dump there. But imagine the cost of that. It's possible. I'm sure that there are several countries around Singapore that if you pay, they would accept their trash. It's about money.
Yeah, that's it.
Thank you very much for the presentation. I understand the secrecy around the concrete technology, but if I would hazard a guess, is your new material a geopolymer filled with exfoliated metakaolinite?
It's related, of course, geopolymers you also get from clays. It's related to geopolymers. But the route we get to the concrete is different from the traditional geopolymer way, yes.
Can you divulge any?
No, trade secret.
Okay.
I'm making money out of that.
So, thank you for the nice presentation. Regarding the nanomolar, you mentioned the sensitivity is very high and accurate, but what about the selectivity? And what is the mechanism for the selectivity? Like,
So I'm sorry, I cannot hear very well.
regarding the nanomolar, you mentioned the sensors are very sensitive and accurate. But what about the selectivity? What if there is...
This is a good question. So, you know, the key to the nanomolar technology is the functionalization of graphene. It's the same with the clays. Okay? So, we have a patented way, again, to do that functionalization, which is different from what people have done in the past. Okay? And that is what guarantees the high accuracy. So all the technology in this sensor comes from the functionalization.
Hello.
Yes.
Thank you for your talk. So you mentioned that if you have a trade secret in your company, then you should not write it down. But then how can you patent it? Or what is the point of having a patent? You don't patent it?
No.
Because you mentioned some sort of patent.
So for certain things we patent, some things we keep as a trade secret. It depends. Usually when it's something related to process, the tendency is not patent that. Because process you can copy, and it's very hard to prove in court that, you know, someone copied you. Okay, because you do a little modification on the process, you may claim there is a different process. So our philosophy is not to patent processes, only patent device or materials, but not processes. Yes?
Thank you, Professor, for this really interesting talk. I have a question regarding the encapsulation you're using for the sand coming from burning the waste.
Yes.
Do you have a stability test where you can, because you know, if you build a house or a building, this is exposed to high humidity, high temperatures.
Yes. Yeah.
I mean, my question is it going to be stable, or after some years, this encapsulation film is going to be decomposed, and then the waste is coming again to the fields?
Yeah. So, you know, one way for you to survive in this business is that you have to have projects. So in Singapore, which is a very harsh environment, as harsh as here, right? Probably more humid, but equally hot. You know, we have several of these things done outside with companies. So we have an entire wall, for instance, which is there being exposed to weather and so on and so forth. And we have like little projects like that, because this is the way you validate the material. Remember, this is a new material, okay? It takes time to validate this with, you know, in real conditions. What we do sometimes is use artificial aging of the material. Okay, so you put in a special chamber that accelerates the process. Okay, so But this is continuous thing. It's like in batteries. In batteries, you have no escape. If you want to prove that your battery lasts 30 years, you have to prove that that the battery is going to survive 20,000 cycles. In construction materials, it's the same thing. You have to, time is the test for them. You can accelerate time, but you cannot accelerate an infinite amount. You can, so these things take time. So patience is a very important thing for entrepreneurship. It's probably the most important thing. Resilience and patience. Yes.
Professor, thank you for your presentation. It was great. I have a related question to what you were saying just now. So, when you want to send this product to the market, of course, many people nowadays is gonna worry about the life cycle analysis, right?
Right.
As you said, it takes time to evaluate. But have you had any approach or any strategy on the end life of this material? Because we know what's the end life of concrete so far and what is the disposal. Yeah. But do you have any idea of how these waste would be treated, or if it can be renewed?
Yeah, the best you can do is do accelerating aging experiments and extrapolate. Okay, so, and that's what we do. And when you do that, for instance, for the concrete, we know that lasts more than 100 years. Okay, but again, these are extrapolations. You have to remember that Portland concrete has been used since the 19th century. So it's tested all over and over. And sometimes some buildings fall. Huh? There are cases of collapse of buildings all over the world because of problems with the concrete. All right? So, as I said, we can estimate, but to measure is going to take real time.
Yes. Thank you, Professor, for your interesting talk. You mentioned that when people arrive to Singapore, you tell them that they are not going to publish articles, but rather they end up publishing patents and they focus more on industry. But also on some of your first slides, you mentioned, you portrayed this, so the divisions, and one of them was theoretical or fundamental. I don't remember exactly. So I guess my question is what's the division? What percentage of the work done there pertains to this area of fundamental?
Right now, so I would say, because the Center for Advanced 2D Materials was created in 2010, so it's very mature. Okay, so this percentage between basic science and let's say applied science shifted over the years. Okay, initially it was 100% basic science, and then now it's probably 60% applied science and 40% basic science. That's would be my guess.
Thanks a lot for the presentation. So I'm interested more in the medical technology application. So for example, you saw about the nanomolar for different type of sensor, right? Lactate, glucose. I understand that the recipe is quite secret, the patented, but I'm wondering how you use or how you choose the biorecognition. So is it less important than the chemical scent that you use in your material? Yeah. Because if we talk about biosensor, usually to make powerful selectivity and sensitivity, bioreceptor is very important, right? Yeah. I'm just wondering, do you consider that bioreceptor in this case is less important than chemical functionalization in your material?
No, I tell you, a good chemist looks at the molecule and more or less knows what has to be because this is a sort of lock and key situation, right? So the molecule trying to measure is like the key, and you have to build the lock, right? But, if you're a good chemist, you look at the molecule configuration and you know what is going to interact with that molecule to provide the electron, because we measure the electron from the reaction of the molecule with the receptor, right? So, in fact, it's amazing, but it's quite easy to figure out what the receptor is. But that's based on experience. We should change that. We should probably do AI as well for that. But, you know, the thing is that we're not trying a huge number of biochemicals because we know exactly the ones the hospitals need, the doctors need. Okay? And it's probably around 10 to 15. So you don't have to be, you know, probing the whole space of chemical products to find out what you need. But it's based a lot on experience.
Thank you, Professor, for your nice presentation. Did you use click chemistry for lock and key?
Use what?
Click chemistry.
Clean chemistry.
Click chemistry.
Clean chemistry.
Click. Click chemistry.
What's click chemistry?
Yeah. Click chemistry.
Define click chemistry.
Last year, you got a Nobel Prize on click chemistry. Okay, anyway, this is not my question. So my question is your sample repeatable and can be used for continuous monitoring of glucose or lactose?
No, it's repeatable. It's very reliable. Everything we have tested, I don't know, 10,000 of times, and it works every time. So it's a very robust thing.
I've been working a lot today, I'd say, in 3 years.
So again, on the nanomolar, with the same device, you can measure multiple compounds, or you have to have a device specific for that one?
So that's a question of engineering. We started with one biochemical. Now we are already at 4. Every time you increase the number of biochemicals, you have to change the electronics. But because, you know, you have to put the contacts in a certain way, and then you have to read the signal in a certain way. So we are now at 4 at the same time. Yeah.
So let's go for the last question.
Last question.
Yes, my question is mostly related to your current cement project. Since conventional Portland cement is manufactured already all over the world by many manufacturers, are you planning your new innovation to license it to existing manufacturers or spin up a new concrete manufacturing company to compete in this market? And if the second, how does the cost per ton of your new material compare to conventional materials?
Okay, good, excellent questions. So I will start answering the last one. Cost is a problem of volume. The more you make, the less it costs to you. Okay? So initially, it's going to be comparable, maybe 10-20% more expensive. But then you gain on the issue of you don't have to maintenance. You don't have maintenance problems. Now, the first question, which is related, is that the first area that we're going to focus is a niche market, which is the repair. The repair market is dominated by people who make epoxy. So it's not a competition with the concrete makers. It's a competition with the specialty chemicals. Now, the profit margin on specialty chemicals is much bigger than in the concrete industry. Okay? Concrete, you make cent on the ton. Okay? In the specialty chemical, you make way more money because it's way less quantity. So our idea is not to go for structural applications. That's not the goal. The initial goal is to go to repair and compete with specialty chemicals instead. Yeah?
So
thank you so much.
So we have plenty of more questions. I would suggest that you come to Antonio and ask him, and you can have a short discussion with him. So with that being said, thanks a lot for this engaging session, and let's thank Antonio one more time.